Here's a problem related to chapter 6. We have a water sprinkler that sprays water over a distance of 30 feet. So we do have a water sprinkler that is just rotating and watering. This is a 30 feet. And of course, then this is 30 feet. What else do we know? We also know, through an angle of 135 degrees. So this angle right here is 135 degrees. So my picture is not so good. Let me extend this just a little bit. Maybe something like this. Okay. 135 degrees. The question is, what area of lawn receives water? So find the area that receives water. Okay. Well, I don't know about you, but for me, the first thing I like to do is to remember to convert the 135 degrees to pi radian. So I'm going to say 135 degrees times pi over 180 degrees. Cancel the degree. Notice that they're both divisible by 45. So I have 3 pi over 4 radian. 3 pi over 4 radian. Okay, so that is my theta. So theta equals to 3 pi over 4 radian. Going to the next page, what else do we know? We know that R was given in terms of feet, 30 feet, okay? So I know area of a sector equals to 1/2 R squared theta, and that equals to 1/2 30 to the second power times 3 pi over 4, and that gives me, okay, I can, 30 squared is 900. Okay, this equals to 675 pi over 2, 675 pi over 2, and that approximately is 1060.29 feet, square feet. So once again, 1060.29, rounded to 2 decimals. Boy, that's horrible handwriting. That is horrible handwriting. Okay. Let me try one more time. 1060.29 square feet. Okay, let's do another problem. This time, we have an engineer that is asked to design a water sprinkler that will cover a field of 100 square yard. So area of interest to be watered is 100 yard squared. Okay, and we want the shape of a we wanted the shape to be the sector of a circle because it's sprinkler. And we want the radius of the sector to be 15 yards. What does that mean? That means that let's say if I'm designing something that is sprinkler that waters like this, okay? I have the area, so this right here is 100 yard squared. And what else did, what else that we know? Um, we know that the shape is, of course, a sector of a circle, okay? And our job is to find out the angle. So find theta, find theta. Okay, we want to find theta. What is it? Is there anything else given here? An engineer is asked to design a water sprinkler that will cover a field of 100 square yards that is shaped of a sector of a circle, of radius 15 yards. So this radius right here is 15 yards. Now that makes it easy. Okay, so what is the, I know R equals to 15. We know A equals 100 yards squared, and we know that area of sector is 1/2 R squared theta. So now I'm going to say 100 equals to 1/2 15 to the power of 2 theta. Okay, and now all I have to do is solve for theta. Divide both sides of this. Let me go to the next page. So I have 100 equals to 15 squared times 1/2 gives me 112.112.5 theta. So theta equals to 100 divided by 112.5, which is going to be roughly, well, let's see. Yeah, it should give me okay, so 8/9, which approximately equals to 2 decimals, 0.89 radian. Okay. If you want to know how many degrees, if you're not, if you want to talk to your customer and you just don't want to talk in terms of radian, what can you do? You can say that 8/9 times 160 degrees over pi, and that roughly equals 8 divided by 9, 50.93 degrees. Okay, let's do one more problem and then we'll move on. Let me go to the next page. Let's see, I have a good problem here. So we do have two pulleys that are connected by a belt in this problem. So we have one pulley in here and a bigger one in here. So these are, of course, circular, and they rotate, they're connected by a belt. They are connected by a belt. So, okay. What is it that we know? It's given that the radius of the larger one is 8. Let's grab different color. So this R is, let's say, 8 meters. And the smaller one is only 2 meters. Only 2 meters. Okay. And we are told that the smaller wheel or the smaller pulley is caused to rotate at 3 revolutions per minute. 3 revolutions per minute. 3 revolutions per minute. And the question is that, okay, if the smaller one is rotating in tree, or it's being caused to rotate by some motor. How many revolution per minute for the large one? So how many revolution per minute for large poly? Yeah. So there's not the different ways of calculating this, but the easier way is to just think of in terms of linear velocity. The linear velocity of both of these polys are the same simply because they're connected by that belt. So, you know, if you, let's say, if you put a dot on the belt, the speed, the linear speed of that dot is the same no matter where that dot is. So I know that V1, the linear velocity of the first one, equals to V2. And the author of the textbook, like other textbooks as well, tells us that V, or linear velocity, equals to radius times omega, which is angular velocity. So I'm going to write down R1 omega 1 equals to R2 omega 2, R2 omega 2. Okay. Well, what is my first, let's say that R1, the smaller one, 2. So I have 2 times the omega, the angular velocity of the smaller poly. We said it was 6 pi radian, 6 pi radian, which is, remember that 2 pi radian is 1 revolution. So if it's rotating, if the rotation is 3 revolution per minute, that means 6 pi radian. And that equals to R2, which was given as 8 meter, okay? And we are trying to find here omega 2. We want to know how many revolutions per minute for the larger poly. And notice how simple it is now. Now I'm going to have 2 times 6 is 12. So I have, if I divide both sides of this also by 8, I have omega 2 equals to 12 pi radian divided by 8. So that equals to 1.5 pi radian per minute. Okay. But since this question is asking that how many revolution per minute, how many revolution per minute, not in this particular question is asking how many revolution per minute, and every 2 pi revolution, every 2 pi radian is 1 revolution. So I'm going to say here that 1.5 pi radian per minute. I'm running out of room, so I'm going to just do this in here, divided by 2 pi, and that gives me 3/4 of revolution per minute. I hope you enjoyed these examples. I'll make more for you really soon.